Let's start by helping Mozart compose a piece of music. Okay. One more. All right. Now just watch and listen, and then I'll explain what we just done in a second. That was actually a Mozart waltz. Now, you probably don't recognize that work of Mozart. It was one of over 759 trillion pieces that he wrote. Confused? Maybe you know your Kershaw listings. That's the complete catalog of all of Mozart. And you know that the last work listed in that catalog is the Requiem at number 626. Now, some numbers are missing and some of them are doubled, but 759 trillion? You know, he died at age 35. That's just not possible. What's the catch here? Mozart and I just used mathematics, probability, to compose that tune. The composition was mathematically generated. More about that in a second. So far, we've really been talking about composing music for a while. Scales, rhythms, transformations, these are all important aspects of composition. But in each case, the mathematics is sort of embedded. It's implicit. The composers aren't necessarily thinking about the math, although now you know that they really are doing some math. What if the mathematics were explicitly used in composition? What would a math-based composition sound like? Well, you heard one already today, and we're going to hear a lot more throughout today's lecture. Today we're going to talk about different ways to explicitly use mathematics and the math tools of mathematics to write and to analyze music. Remember, when we were talking about transformations and self-reference, those things were analogies. You know, Bach didn't use group theory to compose his canons. In fact, group theory hadn't really been discovered and hadn't written down as group theory yet. The canons exhibited similar structures to what would later be called groups. These were powerful analogies. They helped us understand the music better. Today, we're looking at explicit uses of mathematics in musical composition and in musical analysis. And these ways help us gain an even deeper understanding of how math relates to musical composition. Today we're going to take a chronological tour through these literal uses of mathematics in composition, going from 1600 up to modern times. So let's go to the opening music, Mozart's waltz. It's an example of algorithmic music. It's produced by a set of rules, sometimes with chants. And as you saw with the dice, today's was with chants. It's part of an 18th century European tradition called musikalisches Würfelspiel, musical dice games. And to quote from the instructions of the Mozart waltz, the goal of this was to compose, without the least knowledge of music, so many German waltzes as one pleases by throwing a certain number with 2 dice. It's almost like a musical paint-by-number sort of thing. And you get a different result every time, or nearly every time. So how did they make the music sound good? Well, the idea was to compose a large number of measures, all in the same key, and then to make the measures harmonically interchangeable. They were sort of like puzzle pieces, but many different pieces could fit in a particular place in this puzzle. And then they would write out a chart with instructions on exactly how to pick from these measures. Then they'd sit back and watch the musicians roll the dice and play a new piece every time. It's sort of like an 18th century parlor game. Let's look back at this opening waltz. The instructions say, well, to choose measure 1, I was supposed to roll 2 dice. I got a 4 and a 5. Add them together. That gives us a 9. And then find the 9th entry in that column. That particular one was 119. And then I'm supposed to go to the table of measures and look for measure number 119, and that's going to be my first measure in my new waltz. Now that's just one of 11 possible different openings for the first measure. To get the second measure, I look for column 2. Again, I roll dice, and again, I get something between 2 and 12, 2 for snake eyes and 12 for double sixes. And then I choose the measure appropriate for that. And now there's 11 choices for column 2, for measure 2. So that makes 11 times 11 possibilities just for the first 2 measures. The opening waltz, well, I happen to roll the following sequence of numbers: a 9, 9, 3, 6, 9, 9, 9, 6. Those are the first 8 bars. And then the last 8 bars was a 9, an 11, a 9, 5, 9, 4, and a 6. I was really lucky with the 9s. I don't know why. And that gave us the following measure numbers. And those were the measure numbers that I was supposed to pick from the list of measures that Mozart wrote. Let's hear it again, now that we know exactly how it was constructed. It's actually even a little bit more complicated than that, because Mozart didn't write this for violin. He actually wrote it for piano. And there's a bass line. There's a line for the left hand on the piano. But what if we want to hear more possibilities? If you want to hear more possibilities, instead of taking the time to roll out dice, write out the score, and then play it, there are online sites that will generate them and play them and show you the music very quickly. So let's actually count the number of waltzes that Mozart was composing in this. And to do that, we need something called the multiplication principle. Now, you might know a simple version of this. If you have 3 shirts to choose from and 4 pairs of pants, that gives you 12 possible outfits, because the 3 times 4 is 12. If you had 3 shirts, 4 pants, and 2 belts, now you have 24 different outfits. You multiply those numbers. Let's apply that to Mozart's algorithmic waltzes. Now there's 11 choices for each of the bars, because the dice can roll anything from a 2 to a 12. And there's 16 different bars, different measures to choose. And so it's like having 16 different parts of your outfit. And so you have 11 times 11, 16 times. And when you do that multiplication, 11 to the 16th is 4.5 times 10 to the 16th, roughly. And that's 45 quadrillion. Not so fast. You see, Mozart didn't actually have all of those possibilities. If we look closely at the 8th column, the 8th measure, if you roll a 2, you get measure 30. If you roll a 3, you get measure 81. If you roll a 4, you get measure 24. But when you look at those measures, all those measures are exactly the same. The roll doesn't matter at all. You'll always get the same thing for your measure 8. In other words, there aren't 11 ways of choosing measure 8. There's really only one way to choose measure 8. Similarly, the last measure of the piece, the 16th measure, there's really only 2 choices. So now we have to incorporate that into our analysis. And now, so instead of 11 to the 16th, 2 of those 11s become a 1 and a 2, and then we have 14 11s. And so the number we get is 2 times 11 to the 14th, and that is 759 trillion and a few more. It's actually a number that's larger than the US national debt. It's hard to find a number that's larger than the US national debt, but we've done it. Now, is each one of those 759 trillion compositions, is each one of those equally likely? No. You see, when you roll 2 dice, what happens? The odds of getting snake eyes, double 1s, the odds of that happening are 1 in 36, just about a 3% chance. The odds of rolling a 9, on the other hand, well, you could roll a 4 and a 5 and a 4, a 3 and a 6 and a 3. It's 4 out of 36. It's 1/9, about 11% chance of rolling a 9. You're much more likely to get some measures than others. Actually, 7 is the most likely sum. 7 happens about 1/6 of the time, about 17%. The measures listed in the middle of the table are most likely, and the measures listed at the top and the bottom are least likely. Now, I happen to roll a lot of 9s. That means the piece you heard was actually very unlikely to come from this process. Mozart wasn't the first to compose algorithmic music. The first attempt that I know of was Giovanni Andrea Bontempi in 1660. He wrote something called A New Method of Composing for 4 Voices, by means of which one thoroughly ignorant of the art of music can begin to compose. You can see how this is like a paint by number. This is people with no composition skills can use these tools to compose music. It was a fun game. The idea was to make composing easy and fun. Now, are these compositions real music? That's a good question. In 1757, Johann Philipp Kernberg wrote the ever-ready Polonaise and Minuet Composer. Now, this was not just for a couple of lines, but for 2 violins and piano. And now, like Mozart's later work, Mozart's work is of 1787, he used rolls of dice to determine which measures, and all of those measures were pre-written. Other composers jumped on the musical dice game bandwagon. Joseph Haydn did so. C.P.E. Bach, that's Johann Sebastian's son. He was one of 20 or more kids that Bach had, and he was the one who wrote the note about Bach's death. There were other composers as well. Now, in our modern age, we can use computers to produce such music, and we can generate these results very quickly and play them. You wouldn't have to sit in the parlor and keep rolling dice. These Baroque and classical examples of math-based composition are much more tame than what we're going to see later on, the later uses of mathematics in music. Remember back in Lecture 5, we talked about the co-evolution of composition and tunings. The 19th century continued the progression toward atonality. Remember, this was having no tonal center, no main key, no note that you kept coming back to again and again, that you probably started the piece and ended the piece on. Throughout that century, they were moving away from this reliance on a single scale or multiple related scales. By the time we get to 1900, composers were really challenging the notions of what is music. In 1885, Franz Liszt wrote Bagatelle sans tonalité, a bagatelle with no tonality, so intentionally avoiding this sort of tonality. In 1894, Claude Debussy wrote Prelude to the Afternoon of a Faun, which again pushed the boundaries of avoiding tonality. Now, this music was not always well received. In 1913, Igor Stravinsky premiered his Rite of Spring. It's a ballet with orchestra, and the premiere was at a new theater on the Champs-Élysées in Paris. During the performance, audience members argued out loud about the raucous music with strong accents off the beat, bum, 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 just like that, and sort of seemingly random accents, and the radical choreography by Nijinsky. Now, perhaps they were spurred by hot weather, the fact that many of the people in the audience were tourists, the fact that, whatever the causes, they actually came to blows over this, and it devolved into a full-blown riot. Police were actually called in, all over an artistic performance, the Rite of Spring. This represents sort of nearing the end of the increase in dissonance, using intervals that are not prevalent in the overtone series. There were less reliance on standard scales and keys. And this was finally taken to its logical extreme by Arnold Schoenberg with 12-tone music in atonality. And so let's look at that. Schoenberg was born in Vienna in 1874. He played the violin and the cello, and by 1909 he had arrived at these ideas of atonality. He did so with a couple of pieces. One was 3 pieces for piano, which is Opus 11, and the other is a song cycle written around the same time. Now, if you think about the art world, this is right around the same time as the rise of Cubism with Picasso and Braque. Schoenberg was revolutionary in terms of his composition and in terms of performance. He founded the Society for Private Musical Performances. At the Society, there were no critics allowed, there was no advance program announced beforehand, and there was no applause after the pieces. Now, by 1920, he had teamed with 2 of his students, Alban Berg and Anton Webern, and they formed what they like to call the Second Viennese School. Their implication in calling it the Second Viennese School was that they were the natural heirs to Haydn, Mozart, and Beethoven, who would be considered sort of the First Viennese School. Now, all music theory up to that point had really assumed tonality. It assumed that there was a primary key, a foundational note or scale. And by design, some of those notes were more prominent than others. Schoenberg had to search for and to find a replacement for the structure that tonality provided, and he found it in math. His work used the mathematics from Lecture 8, things about group theory, especially things like Z12, the group with 12 elements in it, and transformations, inversions, retrograde inversions. And those ideas are all very key in Schoenberg's work. His goal was to avoid any sense of tonality, to avoid scales, avoid relying on a specific set of notes, avoid the tonal center, to not return to a particular note. His solution was to force himself to use all the notes with equal frequency. He started with a tone row, using each piano note once. We're thinking modulo octaves, so he's using each of the 12 notes once, but he hasn't decided which octave the A might come from. And he's looking at C. For C, it could be any other octave. And he's doing this in a serial way. The tone row is sort of the foundation of a series of tones. In 12-tone music, no tone dominates. That's why we call it atonal music. And he did this by structure, intentionally. Schoenberg actually preferred the word pantonal, not atonal. Pantonal meaning sort of a synthesis of all of the keys, not avoiding any one key. So let's see if we can crudely demonstrate Schoenberg's methods with a simple piece. Instead of working with 12 notes, let's work with 5 notes. And now mathematically we're going to think about working modulo 5, looking at the remainders when you divide by 5. And so those numbers would just be 0, 1, 2, 3, and 4. Now let's randomly order these 5 notes. Let's choose 2, 3, 1, 0, 4. And now we're going to transpose. We're going to make sure we start at 0. And so let's add 3 to each one. So we add 3 to 2 and we get 0. Remember, we're working mod 5. 3 plus 3 is 6, which gives us a 1. 3 plus 1 is 4. 3 plus 0 is 3. And 3 plus 4 is 7, which gives us a 2, working mod 5. So that's our tone row. That's row 1, 0, 1, 4, 3, 2. And now let's write down the transposition of this, the retrograde transposition, and then finally we have to translate these into notes. We're translating the numbers into notes. When we do that, let's think of A being represented by 0, B is 1, all the way through E is 4. And now we have to choose things like the note lengths, which octave we're going to pick these notes from, the rests. So we're going to do that, and I've written out a piece of music. And by design, once we have this chart, each note appears exactly once in each row. And when we write our music based on this, we get to choose the note values and how long and put rests in when we want. Now, there's an important note about this. Because I chose just 5 of the notes on our scale, it's violating a key principle of Schoenberg. You see, he used all 12 notes equally likely, and I've completely ignored 7 of them. But let's hear what we have here. When we take this and we play it, it sounds like this. That should give you some idea of the methods that Schoenberg was using. But now let's turn to the actual 12 tones that he was working with. So Schoenberg and his colleagues used a more complex version. It's the same ideas, but with 12 note names, A sharp, all the way through G sharp. And what we're going to hear is we're going to hear something from Opus 23. There's 5 piano pieces, and we're going to listen to the 5th one. The tone row that Schoenberg was using in this composition is the following. He got these numbers, and then those corresponded to these notes. And these are the notes you'll hear at the very beginning. But before we get to the music, we have to add the transformations. So he took the tone row, he took the inversion, the retrograde inversion, and all of these weren't enough. And so what he did is he took that tone row and he used that tone row, he used the inversion of that tone row to get the first column. And then he wrote out the transposition of the original tone row along each of the rows. And so for instance, one of the notes on that first column was then a 3, and so that's transposing up 3 half steps from the original tone row. And if you look, the row with 3 starting it is exactly 3 numbers above the original row. Now he adds one more layer of complexity before he gets to the actual composition. He now has 12 rows to work with, and now he takes each one of those rows and writes out the inversion, the retrograde, and the retrograde inversion. And now he has 48 different rows to work with. And by design, because of the mathematics, each note appears exactly once in each one of those rows. Tonality is intentionally avoided. No note is more important than the others. So we're going to listen to the opening of the 5th piece of Schoenberg's Opus 23, 5 pieces for piano. Remember, his goal here is to explicitly avoid tonality, the predominance of any single key or scale, and he did this using a mathematically based tone row system to ensure that in every group of 12 notes, each note appears exactly once. And remember the tone row here, starting with C sharp, A, B, G, all of those notes. If you look carefully at the right hand of this piece, it's those 12 notes exactly in a row. Tonality was successfully avoided by Schoenberg. So let's quickly just listen to these first four opening bars where you can hear the tone row explicitly in the right hand. Let's listen to that. And now let's listen to that in context of the larger piece. Schoenberg continues using various lines created from these transformations, from these 48 rows that he has based on the tone row, and he's forcing himself to use all those notes equally, always avoiding tonality. So here's the fifth of the 5 pieces for piano by Schoenberg. So let's look at the attitudes toward Schoenberg, because there's really nothing easy about Schoenberg, or really any of the serial 12-tone compositions. They place heavy demands on both the performer and the audience. They're really cerebral. They're pushing music to its furthest limits. If you look up in the Oxford Dictionary of Music, it says in its entry on Schoenberg, and I quote, "His greatness lies not only in his own music, but in his artistic courage and in his powerful and continuing influence on 20th century music. He is likely to remain always a controversial, revered, and revolutionary musician." If we look at other composers, they were all listing these 12 notes out, and they were listing these 12 notes out, starting with the first one and then going through these 12 notes. They were all doing about the same thing, composing their serial 12-tone music. I want to look at an alternative but similar system, because it has something that's going on in modern times that's very interesting related to it. You see, for Schoenberg, he would write out all the 12 notes, and when we think of these in numbers, there's 0 through 11, and he would write those out, and it's always in reference to sort of the starting point. So 0 and then 4 and then 6, 3, 1, always in reference to the starting point. An alternative way of doing this is to pick a starting note and then to go up 4 half steps, and then to use that as your reference point and go up 2 half steps, to use that as your reference point, go down 3 half steps. It's sort of like bootstrapping that we did when we were tuning things. Now, there's a reason that the 12-tone folks wouldn't have liked this system at all, because it's hard to tell if you've duplicated notes, so it's not very effective at avoiding tonality. But there is an upside to this that came out just in the last few years, and it has to do with numerical encoding of a melody and making that melody searchable. Now, most classical music, most concert music, is now in the public domain. And around 2006, a teenager named Edward Guo, who's a violinist and a pianist, he decided to create an online database of classical sheet music so that everybody could have access to this free and online. And he made it into a wiki so everybody could add music as they saw fit. This is now named the International Music Score Library Project. You can find it at imslp.org. And now, another teenager used this to create a classical music melody search. It was a Russian math student and music lover named Vladimir Viro who encoded all of these musical parts in this alternative to Schoenberg's system, where instead of referencing the first note, he's telling you how far to go from that note to get to the next. He used the IMSLP, the music database, to digitize lots of music. Let's see exactly how this works. So suppose a melody pops into my head. I'm not sure from where. Somehow your brain stores music. We're going to talk about that in lecture 12. But suppose the following melody pops into my head. And I just can't seem to remember where this melody is from. What I can do is I can go to Vero's search engine, it's at peachnote.com, and I can type in the notes, not how long they are, but just the notes. And what I would type in is this. And you can actually see on the search engine, you can see that it's encoding that as 66. 66 is the piano key. I started on the 66th piano key, and then it encodes it as -2, -2, -1, -2. And what that's telling you is how many half steps to go up or down to get to the next note. Now, he's completely ignoring rhythm in the same way that Schoenberg and the 12-tone composers ignored rhythm completely. When you hit return, this is what you get. It tells you that this particular note pattern appeared in several places. It even shows you a timeline of when those places happened. And in particular, it shows you that it was Tchaikovsky's Fifth Symphony. It even provides you a link to the score. So let's look at the score. And in fact, we found the melody. It was Tchaikovsky's Fifth Symphony that I was thinking about. Let's play it in its original. Now, it didn't search. In fact, it found it even though the key was wrong. It didn't search 66 and then up and down from there the changes in pitch. It just searched the changes in the pitch. And the brilliance of that is that it can find it no matter what key you're working in. And so it was able to find this particular piece. It was able to find it as Tchaikovsky's Fifth Symphony, even though I had the key wrong. I don't have perfect pitch, so I wasn't sure where it started. The mathematical encoding of this melody, which was very similar to what Schoenberg used, makes this all possible. Let's go back to our timeline, looking at other composers and how they explicitly used mathematics in their composition. In the 1950s, music took a turn back toward mathematics, reintroducing randomness into concert music. This is called aleatory music. This is from the Latin alia, meaning dice. It's sometimes also called chance music. There's actually a version of aleatory music that you probably hear fairly frequently. Wind chimes are a version of aleatory music. Which pitches you hear are sort of chosen at random, not by any person, but by the wind. Now, the most famous composer of chance music, possibly the most influential composer of the 20th century, was John Cage. John Cage was born in Los Angeles in 1912. He died in New York in 1992. He studied at Pomona College with Schoenberg in the 30s, and purportedly, Schoenberg said of this, his only interesting American student, "Of course, he's not a composer, but he's an inventor of genius." Now, it's telling that we get that quote from Cage's version of the events. Cage was known for his radical experiments. He wrote pieces for prepared piano, so he took the piano and he added bolts and screws on top of the strings, and they would bounce around and make songs. He composed for dance accompaniment with Merce Cunningham's group. He composed for pre-recorded tape with TVs. He composed based on Joyce's Finnegan's Wake. He composed for ice sculptures which contained pebbles, and the pebbles would fall onto wires when the ice melted and make sounds. He composed a piece called Organ ASLSP, where the letters ASLSP were taken sort of an idiosyncratic acronym of as slow as possible. One performance of Organ ASLSP began in 2001. It's scheduled to end in 2640. John Cage's most famous piece is probably 4 minutes and 33 seconds. This is a piece with no notes. It's written for piano in 3 movements, and it's timed. The pianist is supposed to sit there for 3 movements that add up to 4 minutes and 33 seconds. I got to perform this a year ago, and an older gentleman in the front row, he misheard the title, and about 2 minutes in, I heard him whisper to his friend, "This is a lot longer than 33 seconds." For me, Cage's 4 minutes and 33 seconds is actually a musical version of a mathematical concept, and that concept is zero. You know, both zero and a piece without notes, these are sort of symbols for nothing. And I think it requires a certain inspiration to realize that you can do something with nothing. You know, zero was essentially only invented twice by the Mayans and the Indians. The other numbers were invented by lots of different cultures. It's actually, in India, it was Pingala, the poet we heard about when we were talking about the Fibonacci sequence. He started to use zero back when he was writing poetry. Cage was the first to see the complete absence of notes as music. Cage had a lot of different influences, and many of these were from the East. India, Japan, Japanese philosophy, especially Zen writings and other parts of Japanese culture. Now, Cage's use of mathematics came in an interesting way. He started composing chants music around 1950. And he sort of moved from being a composer, from creating, to sort of what he would call accepting the results of chance. And he also gave the performer some sort of uncertainty and some randomness. Some compositions require the performer to do random things and then play based on that. There are mathematical questions in here. What kind of randomness is he using? Technically, the question is, what's the sample space? When we were talking about Mozart's dice game to open this lecture, there was a sample space where 7 and 9 were more likely than 2 or 12. And so you could ask questions about Cage's sample space. Now, one of the sample spaces Cage used was actually a Chinese text called the I Ching. It's called the Chinese Book of Changes. If you don't know it, it was described to me by one of my older Chinese relatives as like an ancient Chinese magic 8-ball. Now, Cage would ask the I Ching to compose, and he would compose based on the responses he got from this chart, choosing from the chart the pitches, the rhythms, the tempos, the dynamics, all based on what he got from this chart. One of the results was a 1951 piece called Music of Changes. And the rest of Cage's life, he used chance elements. He used randomness drawn from many different places in his music. In 61 and 62, he used the randomness of star charts to compose Atlas Eclipticalis. In 83, he used the particular rock formations in the Zen temple in Kyoto, Japan, the Ryo-Anji temple, and he used those rock formations to compose a piece. He was really stretching the idea of randomness, and other composers stretched it even further. Charles Dodge composed a piece called Earth's Magnetic Field, where the pitch changes were taken from the changes in Earth's magnetic field, and those changes were due to solar winds. I think you'll agree the effect of this sort of celestial source of randomness sounds, well, it sounds very random. Let's listen to a bit from Dodge's piece. We're going to take one last stop in this mathematical composition after hearing that Dodge piece. And the last stop is spectral music. Now, spectral music comes from a European tradition. And the European tradition was looking at trying to create the spectrum. We remember the spectrum from lecture 2. The spectrum showed you how much of each overtone you're going to hear. And this European tradition was based on that. You can actually see in this graph, right? You can see in the spectrum you have these different peaks at different frequencies. And that was the timbre, how high each one of those peaks were. Mathematically, it was the Fourier transform of the waveform that gave us the spectrum. Remember, the jump rope and the drum heads were showing the different modes that something could vibrate in. Now, spectral music was trying to use different ways of using that spectrum to create music. In one particular piece, Griset's Période, 7 instruments were used to recreate the spectrum of a trombone. So the entire piece led up to the final chord where these 7 instruments were combined to try to recreate the timbre of a trombone. Now there's some versions of using mathematics to compose music that we haven't covered. In particular, there are a lot of computer programmers who use computers to compose, or maybe we should say to compute or maybe program music. One of the most prolific is David Cope, who's done extensive work, including work to emulate Mozart. The algorithms he uses range from fairly simple to highly complicated algorithms, and they're really bordering on a field of artificial intelligence. We're going to save this for lecture 12 when we talk about math, music, and the mind. I do have a little bonus today for the more mathematically inclined. So far we've talked about using math to write music, and this last bit is going to be about using math to analyze music. Now there are a lot of different ways to do this, and different music theorists have used many different methods, including statistics. But maybe the most surprising comes from the recent work of Princeton's Dmitry Timashko. He's working on the geometry of music, and a lot of his work is very, very complicated, both mathematically and musically, but one of his early results is probably the easiest to understand. He looked at the geometry of two-note chords. So let's take a look at that. Now, the geometry of one-note chords is fairly simple. Remember, you have notes A sharp, all the way through G sharp, and then A is really the same thing as the original A, if we're thinking modulo octaves. And so the ends of this wrap around and give you a circle. And so the geometry of one-note chords, which are just single notes, the geometry of that is just a circle. And when we think about the mathematics of that, that's just Z12. It's just like addition modulo 12, where you're looking at the remainders when you divide by 12. Another way of thinking about this is that you could take the G sharp that you ended up at and you could glue it to the A. Or if you got to the A, you could glue the two A's together and paste them together. And that's how you might get this circle. Now all of this is thinking modulo octaves, right? And so we're treating all of these notes as all of the different octaves of C sharp as being the same. Now what if you had two notes? Well then you would get two coordinates, right? So you would have A sharp, B laid out on the X coordinate, and then you would have A sharp, B laid out on the Y coordinate. And each two-note chord would be a spot on these 12 by 12 grid. If you had a chord with a G and a C, you would find that in the G, C spot in our chart. And now, musically, you would have many options for playing that because you could pick the G and the C from any octave you wanted, but those would all be examples of a G-C two-note chord. Now, we have to remember that both the X and the Y axis, these notes are in a line, but we just figured out that that should really be wrapped into a circle. So what happens when we do that? Well, look at everything on the X-axis. Everything in the first column has A's, and everything in the last column has G sharps. And those are supposed to be right next to each other. And so when we tape those so that they're exactly next to each other, we geometrically get a cylinder. But now, look along the cylinder, and now everything in the bottom ring of that cylinder is an A, and that should all connect to everything on the top ring of that cylinder, which is G sharp. And when we connect those, the result is what mathematicians call a torus. It's the surface of a donut. And so we might think that we're done. We might think that two-note chords form a torus. But when we look back at the chart, we see that we've done something wrong. You see, the G-C chord we were talking about earlier, it doesn't appear just in the G, C part of the chart. It also appears in the C, G spot. And so we've really double counted. Our construction of a torus double counts the chords. And so we don't have the geometry quite right yet. These two-note chords don't form a torus. It's actually better than that. So let's see if we can fix this. In order to fix this, we're going to have to get into a little bit of gluing. So before we were gluing the first column to the last column, and we saw that those were supposed to wrap around. But now what we've seen is if we look at like AB is the same chord as BA, and A sharp C is the same chord as C A sharp. If we look along the first row, all of those are really the same thing as the first column. So really we also have to glue the first row to the last column. And that's hard, especially when we look at the direction of the glued edges. You see, the first and the last column are glued together in the same direction. If you look at the arrows are telling you what direction to glue these. But now the first row is also supposed to be glued to both of those. And we're supposed to glue that starting at one corner and ending at the other. So the first row is supposed to be glued to the last column with the bottom left corner glued to the bottom right corner. And you just can't do it. You can't do it physically. If you try this with a piece of paper, you'll have to like crumble it up. You won't be able to do it. But notice that once we've sort of abstracted it to just this rectangle, we really just have abstracted the core mathematical ideas from this musical thing, and now we just have a math problem to do. And so let's see if we can fix this gluing problem. To fix this, remember that there was redundancy. And if you looked closely, the double counting happened on the bottom and the top of these triangles. The bottom triangle contained all of the chords, and the top triangle contained all of those chords again. And so that's where the double counting was. So if we want to figure out the geometry of two-note chords, let's just remove the top triangle. And if we get rid of the top triangle, then we have every chord represented just once. And now we only have two edges we're supposed to glue to each other. We're supposed to glue the bottom edge to the right edge. But again, the direction of that gluing makes that very difficult. And so to fix this, we're going to do something that mathematicians actually call surgery. We're going to do topological surgery on this piece. We're going to cut the diagonal. And we have to remember which way we're cutting the diagonals, because later we're going to want to paste that back together. Right? When you do surgery, you want to stitch the patient back up at the end. So let's cut along that diagonal. And then let's flip the right triangle over. Finally, we have to move that flipped triangle, and then we have to move it into position where we can glue these two solid lines together. And once we've glued those two edges together, once we've finished repairing that, now look what we have. What we have is just a strip. And if you look at the ends tell us how to glue those together, and the ends are telling us we're supposed to glue it together, not like we did originally, not like we would get a cylinder, but in opposite directions. We're supposed to glue the ends together with a twist. We've seen a strip where we're supposed to glue ends together with a twist before. It was exactly the Möbius strip. We saw it in the lecture on self-reference. We saw it in how we constructed the table canon in a way that both players could play it continuously. We just took that strip and we twisted it and we pasted it together. And that's what we're getting from this geometry of two-note chords. We get a Möbius strip. So what does this mean? It means, well, Tomaszko's work shows us that the space of two-note chords has the geometry of a Möbius strip. And any sequence of two-note chords is really just a path along the Möbius strip. This is a new way of visualizing music. If you take anything that has two notes at a time, each one of those pairs of two notes is a particular point on this Möbius strip, and then you can follow the composition by just following a path on the Möbius strip. It's a new way to visualize music. It's a new way to study music, the music of chords that have two notes at a time. So let's look at an example of this. I'm going to play a little bit from Pachelbel's canon. I think this piece is played at nearly every other wedding that I go to. The piece actually has 3 identical violin parts, and each one is delayed 2 measures from the previous. And so each note has to function in 3 different ways. It functions first as the melody, and then it functions as harmony 2 more times. The bass line is probably the most boring part ever written for cello. It is the same 8 notes repeated over and over and over again. I've had cellists just tell me at the beginning of this piece, just nod to me when we're done, because then I'll finish. I don't want to have to read the music the whole time. So in order to visualize exactly how Pachelbel's canon sounds and how it looks on Tomaszko's Möbius strip, I'm going to play one of the violin parts, and we're going to electronically add a bass line. That gives us 2-note chords, and we're going to show you where on the Möbius strip each 2-note chord is. Now, you have to remember that this is a Möbius strip. We're going to show it to you as just sort of a rectangle on the screen, but when you go out the top of the right side, you come back in the bottom of the left side. And if you go out the top of the left side, you come back in the bottom of the right side. That's the twist. That's what makes it a Möbius strip. So here's the opening 16 measures of the Pachelbel canon. It goes on and on like that. If you want to see more of the geometry of chords, I encourage you to look at Tomaszko's website, which has lots of really interesting information on that. Today we went from Mozart's dice games to Cage's chance music to Tomaszko's geometry. In all these cases, we saw that mathematics helps us compose and analyze music. Math also helps deliver it to us in a modern age where we have everything digitized in zeros and ones. And that's what we'll talk about next time. Thanks for joining us.